Diodes are electronic devices that allow current to flow in only one direction. They are widely used in a variety of applications, including rectification, voltage regulation, signal modulation, and power conversion. One type of diode that is commonly used in electronics is the Schottky diode. A Schottky diode, also known as a hot carrier diode, is a type of semiconductor diode that uses a metal semiconductor junction instead of a PN junction to achieve rectification. It is named after its inventor, Walter H. Schottky, who developed the device in 1938. Schottky diodes have several advantages over conventional diodes, including a lower forward voltage drop and faster switching speed. The metal semiconductor junction of a Schottky diode consists of a metal layer, typically made of aluminium or gold, that is deposited onto a semiconductor material, such as silicon or gallium arsenide. The metal layer forms a rectifying contact with the semiconductor, which allows current to flow in only one direction. The metal semiconductor junction has a much lower voltage drop than a PN junction, which allows Schottky diodes to operate at higher frequencies and with lower power losses. Schottky diodes are commonly used in applications where high-speed switching is required, such as in power supplies, voltage regulators, and rectifiers. They are also used in microwave and RF circuits, where their high-frequency response and low noise make them ideal for signal detection and mixing. In summary, Schottky diodes are an important type of semiconductor diode that are widely used in electronics for rectification, voltage regulation, signal modulation, and power conversion. Their metal semiconductor junction provides several advantages over conventional PN junction diodes, including a lower forward voltage drop and faster switching speed. The manufacturing process of Schottky diodes involves several steps, including semiconductor wafer preparation, metal deposition, patterning, and packaging. Here is a brief overview of the manufacturing process. Semiconductor wafer preparation. The manufacturing process begins with the preparation of a semiconductor wafer, typically made of silicon or gallium arsenide. The wafer is cleaned and processed to create a highly pure and uniform semiconductor material. Metal deposition. A thin layer of metal, typically aluminium or gold, is deposited onto the surface of the semiconductor wafer using a technique such as sputtering or evaporation. The metal layer forms the rectifying contact with the semiconductor material, creating the Schottky barrier. Patterning. The metal layer is then patterned using a photolithography process, which involves applying a photoresist material onto the metal layer, exposing it to light through a mask, and then etching away the unexposed portions of the metal layer. Annealing. The wafer is then annealed to stabilize the metal semiconductor junction and reduce any defects or impurities that may have been introduced during the metal deposition or patterning process. Electrical testing. The individual Schottky diodes are then electrically tested to ensure that they meet the desired specifications for forward voltage drop, reverse breakdown voltage, and other parameters. Packaging. Finally, the Schottky diodes are packaged into their final form, which may involve encapsulation in a plastic or ceramic package, wire bonding, and other assembly processes. The manufacturing process for Schottky diodes is similar to that of other semiconductor devices, but with some specific differences due to the unique metal semiconductor junction. Careful control of the metal deposition and patterning processes is crucial to achieving the desired electrical properties and performance of the Schottky diode. The Schottky diode has several important characteristics that differentiate it from other types of diodes, including its low forward voltage drop, fast switching speed, and low reverse recovery time. Let's take a detailed look at these characteristics. Forward voltage drop. The forward voltage drop of a diode is the voltage that must be applied across the diode to make it conductive in the forward direction. The Schottky diode has a much lower forward voltage drop than a standard PN junction diode, typically around 0.30.5 volts, compared to 0.60.7 volts for a silicon diode. This low forward voltage drop means that Schottky diodes have lower power losses and can operate at higher frequencies than p-n junction diodes. Reverse breakdown voltage. The reverse breakdown voltage of a diode is the voltage at which the diode begins to conduct in the reverse direction. Schottky diodes have a relatively low reverse breakdown voltage, typically around 5100 volts for silicon-based devices. This means that they are not suitable for high-voltage applications and must be protected from voltage spikes and other overvoltage conditions. Switching speed. The switching speed of a diode is the time it takes for the diode to switch from the non-conductive to the conductive state or vice versa. Schottky diodes have a very fast switching speed, typically in the range of picoseconds to nanoseconds. This makes them ideal for use in high-speed switching applications such as in power electronics and digital circuits. Reverse recovery time. The reverse recovery time of a diode is the time it takes for the diode to switch from the conductive to the non-conductive state when the voltage is reversed. Schottky diodes have a very low reverse recovery time, typically in the range of nanoseconds to microseconds. This means that they have minimal reverse recovery losses and can switch quickly between the forward and reverse states. Temperature dependence. Like all semiconductors, the electrical properties of Schottky diodes are strongly dependent on temperature. The forward voltage drop of a Schottky diode increases with temperature, while the reverse breakdown voltage decreases. Careful consideration of these temperature dependencies is necessary when designing circuits using Schottky diodes. In summary, the Schottky diode has several important characteristics that make it a popular choice for a variety of applications, including its low forward voltage drop, fast switching speed, low reverse recovery time, and temperature sensitivity. These properties make Schottky diodes ideal for use in power electronics, digital circuits, and high-frequency applications. Advantages of Schottky diodes. Low forward voltage drop, leading to low power losses and higher efficiency. Fast switching speed, allowing for high-speed operation and reduced switching losses. Low reverse recovery time, leading to reduced reverse recovery losses. Lower leakage current compared to p-n junction diodes, can be fabricated in smaller sizes and with lower cost compared to other high-speed diodes, compatible with a wide range of applications, including power electronics, digital circuits, and RF, microwave applications. Disadvantages of Schottky diodes. Relatively low reverse breakdown voltage, making them unsuitable for high-voltage applications. Increased sensitivity to temperature changes, which can affect their performance. Higher susceptibility to ESD, electrostatic discharge, and other forms of electrical stress. Limited availability in certain voltage and current ratings compared to other diodes. Potential reliability issues due to the metal semiconductor interface, which can degrade over time under high current or temperature conditions. Schottky diodes have a wide range of applications due to their unique characteristics, including their low forward voltage drop, fast switching speed, and low reverse recovery time. Here are some of the most common applications of Schottky diodes. Power electronics. Schottky diodes are widely used in power electronics applications such as DC-DC converters, voltage regulators, and inverters. Their low forward voltage drop and fast switching speed help to reduce power losses and improve efficiency. Digital circuits. Schottky diodes are commonly used in digital circuits as clamping or protection diodes to prevent voltage spikes and other transient events from damaging sensitive components. They are also used as high-speed switching diodes in logic gates, flip-flops, and other digital circuits. RF, microwave applications. Schottky diodes are used in a variety of RF and microwave applications, including mixers, detectors, and frequency multipliers. Their low forward voltage drop and fast switching speed make them ideal for high-frequency operation. Solar cells. Schottky diodes are often used in solar cell applications as blocking diodes to prevent reverse current flow and improve the efficiency of the solar cell. Automotive electronics. Schottky diodes are used in a variety of automotive electronics applications such as voltage regulators, power steering systems, and engine control units. Their low forward voltage drop and fast switching speed help to reduce power losses and improve efficiency. Consumer electronics. Schottky diodes are used in a variety of consumer electronics products such as power supplies, battery chargers, and LED drivers. Their low forward voltage drop and fast switching speed help to improve efficiency and reduce power consumption. Overall, Schottky diodes are used in a wide range of applications due to their unique characteristics, making them a popular choice for many different types of electronic devices and systems.